All right. Okay. Good afternoon. Good afternoon. We'll start. First, can you confirm whether I am audible? Audible, right? Okay. So I hope my audio and video is clear for all of you, right? We'll start. Right. Listen. So last week, we finished thermodynamics, right? We finished thermodynamics. So today we are stepping into hygrometry, right? The next lesson, let's subheading we have in thermal. And about the monthly plan, today we are starting hygrometry. No, today we are starting hygro, right? And then after hygrometry, we'll start heat conduction. Heat conduction is also called thermal conduction. And the last week of the month, we'll be doing thermometry. And this will be the last month we are spending with thermal, right? So by the end of March, we'll be finishing all thermal parts. We'll be finishing all thermal parts, right? And from the reverse class, right? From the reverse class, we are doing matter and radiation. We are doing matter and radiation, and radiation part is already covered last week. And the next week means this Saturday, we'll be starting the next part of radiation, that is called black body radiation, right? So next week we'll be starting this Saturday we'll be starting black body radiation, right? And during the month, matter and radiation will also be covered in the reverse class, right? So those are the monthly plans for this month. By the end of March, we will be covering both thermal and matter and radiation, right? Okay, after thermal, in this class, this in regular class, I'll be starting gravitational fields, and in the reverse class, I'll be starting current electricity, right? That's the plan. Gravitational fields here and current electricity, they are in the reverse class, right? Okay, then let's jump into the lesson. Give me 1 second. Right. Okay, let's start. Okay, put down the heading as hygrometry. 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 Right. Listen now. Listen. In calorimetry, I have told you what a metry is. What's the meaning? Metry. Metry means metry. Metry means that is about a measurement. We are going to measure, right? Measuring. Metry means that. What's the meaning of hygro? If anyone have come across the word, what's the meaning of hygro? What does that mean by hygro? Right. Hygro. No idea. Hygro means, I think live is shared to the groups, right? 1 second, let me check. it's shared now. All right, listen. Right. Hygro means that is all about moisture or humidity or simply water vapor. Right? That's the meaning. That's the meaning of word hygro. Now, if I separate this into two, hygro means that is about humidity. Humidity. Right? What is humidity? Humidity is all about moisture. Moisture means that is uh, a measurement that we take about the amount of water vapor availability. Amount of water vapor, right? Humid means moisture, right? Moisture means that is about the amount of water vapor. That is about the amount of water vapor. That is about the amount of water vapor. And metry means we know. Metry means it is about measuring. It is about measuring. Then basically in hygrometry, what we are going to do is we are going to measure the amount of water vapor available, right? Water vapor availability in atmosphere, in environment, right? So basically hygrometry is a study on amount of water vapor, right? Or rather measuring the amount of water vapor. Got it? Okay, write down below. Hygrometry is the study on 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 measuring hygrometry is the study on measuring hygrometry is the study on measuring amounts of water vapor, measuring amounts of water vapor, measuring amounts of water vapor. It's a study on measuring amounts of water vapor, measuring amounts of water vapor. Within brackets, humidity, within brackets, humidity, humidity in atmosphere, humidity in atmosphere, humidity in atmosphere, humidity in atmosphere. Right, listen. So when comes to the water vapor availability in atmosphere, right? First, let's see how water vapor is collected to atmosphere, or how water vapor is coming to atmosphere, right? When comes to water vapor availability in atmosphere or any other environment, that is due to two main reasons or two main processes, right? One is called evaporation, right? And the other one is called vaporization. Basically, because of evaporation and vaporization, water vapor is coming to the atmosphere, right? I am pretty sure that you have heard about these two words before as well, right? But I'll be discussing all the differences, similarities, and what vaporization is and what evaporation is here also. But I'm pretty sure that you have heard about both of them, right? Up to some extent. But here in A level physics, we'll be discussing few more things as well. But in O levels, I know you have heard about it, right? Okay, now my point again is, if you think of the methods, the processes, water vapor is collected to atmosphere. Main two processes are evaporation and vaporization, right? Then let's see what are the differences and the similarities, right? Kind of a comparison between evaporation and vaporization, right? As the next point, write down. As the next point, write down. Water vapor is collected to atmosphere. Next point. Water vapor is collected to atmosphere. Water vapor is collected to atmosphere. Water vapor is collected to atmosphere. Mainly due to water vapor is collected to atmosphere. Mainly due to water vapor is collected to atmosphere. Mainly due to evaporation and vaporization. Mainly due to evaporation and vaporization. Mainly due to evaporation and vaporization. Right. You can split your page into two and draw table like this. One side is evaporation, the other side is for vaporization, and we'll be comparing these two in point 4. Right, take it down. Right, and this is something you can engage well. Right, this is something you can engage well, because up to some extent, right, up to some extent you have heard about this in oils as well. Tell me this. Now, if I ask about temperature, right? If I ask about temperature, one process out of these two happens at any temperature, and one process happens only at a certain point, right? Which process happens at any temperature? I haven't turned on the recording on Zoom. So if you notice the recording is not on, please remind me. If you notice that the recording is not on, please remind me. Right. Which process out of these two takes place at any temperature? No idea. Right. Let me explain this way. Now, when it comes to evaporation and vaporization, both are happening due to increasing temperature of molecules. Right. Both are due to increasing temperature of molecules. Right. Simply, in both vaporization and evaporation, what happens is that is all about leaving the molecules with high temperature from the liquid surface. That's the process, right? They are leaving the liquid surface, right? And both are doing the same. Both are doing the same, but there are differences and as well similarities, right? When it comes to evaporation takes place at any temperature, right? Now, as an example, from water bodies, rivers, lakes, tanks, ocean, and maybe ponds, or any other water bodies, right? From any other water bodies, and even from leaves of trees, from water bodies, water vapor is leaving. Water vapor in the sense molecules. Water vapor molecules are leaving that liquid surface at any temperature. That process is called evaporation. And when it comes to vaporization takes place only at boiling point. That is specifically at boiling point, right? Which means that is what you see when you boil water. When you boil water at 100 degrees Celsius, right? Then you can see steam, right? You can see steam. We can see steam in a kind of a smoke whitish color, right? We can see smoke. We can see steam. Steam is water vapor. Steam is also water vapor, right? Difference is vaporization is the process which occurs only at the boiling point, and evaporation is the process which occurs at any temperature, right? And for bio students especially, right? You know this thing from O levels, from A levels as well, not O levels, from A levels as well, right? I know you have evaporation and vaporization, no? Right? So connect these things with what you have learned if you have already learned about those things in bio, if you are doing bio, right? For combined math students, you have to start everything from here. Doesn't matter whether you know this from O levels or not, that doesn't matter. And this is the difference. Both are about leaving the water molecules, not water, liquid molecules with higher temperatures, right? And evaporation takes place at any temperature, but vaporization is only at boiling point. Okay, first point, write down. First point, this side. First point, this side. Occurs at evaporation, no? Evaporation side occurs at any temperature. Occurs at any temperature. Occurs at any temperature. Right? And vaporization side occurs only at boiling point. Vaporization side occurs only at boiling point. 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 Right. Next point. Respond these questions and engage with the lesson. Right. Listen. One process out of these two is visible and one is invisible. One is visible and the other one is not visible or invisible. What is a visible process from these two? What is a visible process from these two? Use your knowledge and use what you know. Because this is not something whole new to you, something you know. That's why I'm always trying to connect this with what you know already. Right? Tell me, what is visible out of these two? What process is visible? Vaporization. Good. Vaporization is visible. Vaporization is visible, but evaporation is not visible. Now, when you look at a river, right? Can we see the evaporation? No, we don't see anything. Right? Now, even if I keep some water, say, in a glass, right? So after some time, it will be evaporated. Right? But we don't see anything. Evaporation is not visible, but vaporization is visible. When vaporization takes place, you can see that stream, right? Steam is evaporation. Steam is vaporization. Then only vaporization is visible, right? Second point. Evaporation side, not a visible process. Not a visible process. Not a visible process. Not a visible process. The ones on YouTube also, you can put your things, put your answers, put your questions, doubts, so any answers, responses, everything to the live chat. Right? Evaporation side, not a visible process. Vaporization side, a visible process. Vaporization, a visible process. A visible process. Okay, next. Listen. Next one. During one process, right? During one process, system gets cooled. And during the other process, system stays at a constant temperature. Tell me, at which process occurs at a constant temperature? Which process occurs at a constant temperature? Which process out of these two occurs at a constant temperature? Which occurs at a constant temperature? Quickly. Which occurs at a constant temperature? Evaporation. Vaporization. It's actually vaporization. Because vaporization occurs only at boiling point, right? And vaporization is a state change. you know calorimetry, right? So connect this with calorimetry. Vaporization is a state change. That's a state change. At any state change, right? During the state change, temperature of the system remains constant according to Q equals ml, right? That is what we learned in calorimetry. Got it? Got the point? That is what we learned in calorimetry. Then during the state change, temperature of the system remains constant, which means vaporization occurs at a constant temperature. But during evaporation, system gets cooled because molecules with higher temperatures are leaving the surface, no? So system gets cooled, right? Then evaporation side, third point in evaporation side, write down. System gets cooled. System gets cooled. System gets cooled. System gets cooled during the process. 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 And vaporization side, system remains at system remains system remains at constant temperature. System remains at a constant temperature. System remains at a constant temperature during the process. System remains at constant temperature during the process. System remains at constant temperature during the process. Right? Okay, next point. Listen. One out of these two occurs or happens only at the surface, and the other process occurs throughout the volume. Which one occurs at the surface? Which process occurs at the surface? Only at the surface. Which process occurs at the surface? Evaporation. Yes, it's evaporation again. It's evaporation because the reason is when it comes to vaporization, if I compare this with vaporization, we know before the state change starts, each and every molecule, each and every particle of the system comes to same temperature. Then all of them comes to the boiling point. Right? All of them comes to the boiling point. Then all the molecules, all the particles of the system are at the same temperature. Then any particle can be vaporized at any given time. Right? But when it comes to evaporation is only at the surface, because now when temperature of molecules are different, higher the temperature, the such particles are coming up, right? Because when temperature increases, density decreases, no? Because of the decrease of density, they comes to the surface, and from the surface they evaporate, right? So therefore evaporation is at the surface only. When it comes to vaporization, that is not only at the surface, that is throughout the volume, right? Next point, evaporation side, write down. Evaporation side occurs only at evaporation side occurs only at the surface, occurs only at the surface open to atmosphere. Occurs only at the surface open to atmosphere. Evaporation occurs only at the surface open to atmosphere, right? And vaporization side occurs throughout the volume. Vaporization side occurs throughout the volume. Vaporization side occurs throughout the volume. Focus throughout the volume. Right. Next one. Next one. Listen. One process of these two is highly dependent on external environmental factors. Right? External environmental factors like wind speed, right? Wind speed and humidity, right? Likewise. And the other process is not that much dependent on the environmental factors, outside the external environmental factors. What is depending? What is depending on environmental factors? Any thoughts? Which process of these two, which process out of these two is dependent on external factors or external environmental factors? What do you think? It's evaporation again. It's evaporation again. When it comes to evaporation, evaporation is very sensitive and it is sensitive to wind speed, moisture. Moisture means amount of water vapor in the atmosphere. It changes day by day. But when it comes to vaporization, it is not that dependent on environmental factors. Even though the wind speeds are different, boiling point is always at 100 degrees Celsius, right? And sometimes moisture can be different, right? But still, boiling point is at 100. Boiling point changes only with a difference in pressure, right? Difference in pressure, or we can say altitude, right? With altitude or pressure only, boiling point changes, not on other environmental factors, right? Evaporation side, next point, evaporation side, highly dependent on, highly dependent on, highly dependent on, highly dependent on, highly dependent on external, dependent on external environmental, highly dependent on external environmental conditions, highly dependent on external environmental conditions, right? Within brackets, write down wind speed, within brackets wind speed, comma humidity, wind speed, humidity, wind speed, humidity, right? Wind speed, humidity, right? Vaporization side, write down, doesn't depend on, doesn't depend on doesn't depend on, doesn't depend on external, doesn't depend on external environmental, external environmental conditions, right? Now next point is common for both, right? And use a red pen and write down as a common point for both. Use a red pen and write down as a common point for both. Write down both evaporation and vaporization, both evaporation and vaporization, both evaporation and vaporization are results of both evaporation and vaporization are results of are results of leaving water molecules leaving water molecules leaving water molecules leaving water molecules with higher temperature with higher temperature with higher temperature and higher kinetic energy with higher temperature and higher kinetic energy with higher temperature and higher kinetic energy higher temperature and higher kinetic energy, right? Then you can close the table. You can close the table. Close the table. Right? Listen. And the impact on evaporation by wind speed and humidity is like this. It is like this. Higher the wind speed, don't write. Higher the wind speed, higher the evaporation. Higher the wind speed, higher the evaporation. Right? And higher the humidity, lower the evaporation. Because humidity is high means humidity is the measurement on amount of water vapor available in the environment, no? Right? Then higher humidity means higher amount of water vapor is already available in that atmosphere. Then leaving of new water vapor to the atmosphere is demotivated. That is demotivated. So it will be decreased, right? So that's why when humidity increases, evaporation decreases. When humidity increases, evaporation decreases. Okay, write down below with a red pen again. Write down below with a red pen. First point, next point. Higher the wind speed, write down. Higher the wind speed. Higher the wind speed, higher the evaporation. Higher the wind speed, higher the evaporation. Higher the wind speed, higher the evaporation. Right. Next point. Higher the humidity. Next point. Higher the humidity. Lesser the evaporation. Lesser the evaporation. Higher the humidity, lesser the evaporation. Okay. Right. Listen. So before moving on to the next part, any questions up to here? Any questions up to here? Is it all clear? Raise your hand if it is clear up to this point. We did nothing, we just compared between evaporation and vaporization. Okay, then. Right, good. Then as an next heading, write down water vapor. Next heading, water vapor. Right, write down below. Write down below. There are two main forms. There are two main forms. There are two main forms. Two main forms of water vapor. There are two main forms of water vapor available in atmosphere. Water vapor available in atmosphere. Available in atmosphere. Right. First one, saturated vapor. Write down. Saturated vapor. And the second one, unsaturated vapor. Saturated vapor and unsaturated vapor. Take it down. Now let's see. Now let's see. What does this mean? One by one. Right? As number one, write down again saturated vapor. As number one, write down again saturated vapor. Saturated vapor. Look at the board. Look at the board. Now, this is about saturated vapor. It is like this. Listen. Let's assume we have a water basket, a beaker, or something like this, and it is closed from the top. It is closed from the top. Right? Now, because of evaporation, listen, because of evaporation, some of the particles from this water layer, liquid layer, goes to atmosphere. Goes to atmosphere like this. Like this. Right? And the beauty of this is, if this is called the water vapor layer. This is called the water vapor layer or the vapor layer. Right? The beauty is this vapor layer, if this vapor layer has acquired the maximum possible number of water vapor which can be kept at this space, which can be kept at that medium, that is called saturated vapor. Right? Which means basic idea of this is, if this layer, if vapor layer has gained or has acquired the maximum possible number of water vapor to the vapor layer, right? It's called a saturated vapor. Saturated means maximized, no? Saturation means that's a top tier value, maximized, maximum value. That's the whole idea, right? That's the whole idea. That is called saturated vapor. And in this case, listen, in this case, what happens is, when this is in this equilibrium, this is an equilibrium. When this is in this equilibrium, if n number of molecules comes into vapor layer, right? Simultaneously, same n number of molecules are put down from water layer as well, right? What's the meaning? Meaning means, now if there were molecules with higher temperatures, right? Their temperatures are high, right? Their temperatures are high. With higher temperatures, they are like rapidly going to this vapor layer, rapidly going to vapor layer. And once the maximum possible number of molecules which can be kept at the layer is reached, right? That number remains same. That number remains same. But even after that, if there are molecules with higher temperatures and if they try to come to the vapor layer, what happens is if n number of such particles comes into vapor layer, right? Then at the same time, concurrently, same number of particles are put down from vapor layer, right? Because once the saturation is reached, which means that is at the maximum values, right? That is at the maximum values, right? Now, as an example, let's say there are 100 molecules here, and 5 came from the liquid layer again, right? Then to make this 100, when this 5 comes, right? The molecules with low temperatures, less temperatures, right, are put down from the vapor layer to counterbalance this, to balance this, right? So such gas is called, right, or such vapor is called a saturated vapor, right? That's a saturated vapor. And in gases, I told you, when it comes to gases laws, to which kind of gases they are valid? For saturated gases, so unsaturated gases. We explained on the expansion of gases. Tell me, from your knowledge on gases, right? From your knowledge on gases, tell me. Tell me. Gas laws are, listen, gas laws are valid only for gases, normal gases, right? Gas laws are valid only for the normal gases. Normal gases in the sense they are for the unsaturated gases, not the saturated ones. Saturated gas laws are right? I think we mentioned in red under gas laws. You can go back to the gas tube and check. All gas laws are valid only for unsaturated vapor, normal vapor, unsaturated vapor, right? Not the saturated. Because when it is saturated, it is going to behave in a different manner, right? Different manner, and it is not following any gas laws. Gas laws in the sense, Boyle's law, Charles, pressure, and PV equals nRT, right? Right? Those are the gas laws. They are only for unsaturated vapor, right? Now, take on the next heading as saturated vapor. Saturated vapor. Saturated vapor. Right? And below that, write down. Below that, write down. Before writing down, can you take down the diagram? This is called a dynamic equilibrium. Right? This is called a dynamic equilibrium because, listen, because the number of molecules which are in vapor layer is constant even though molecules are switching between these two, right? Right, that is called a dynamic equilibrium. Dynamic equilibrium, right? Take down the diagram first. Diagram. Take down the diagram. right? Okay, finish. Write down below. Write down below. Write down below this one. A vapor. A vapor. Write down below. A vapor. A vapor in a dynamic equilibrium. 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 Dynamic equilibrium. In its liquid phase. In its liquid phase. In its liquid phase. In its liquid phase. By holding. By holding. By holding the maximum number of. By holding the maximum number of. By holding the maximum number of vapor at a given temperature and pressure. At a given temperature and pressure. At a given temperature and pressure. At a given temperature and pressure is called saturated vapor. Is called a saturated vapor. Is called a saturated vapor. Is called a saturated vapor. Right? Right. Now, even though this number of water molecules or vapor molecules stays same here, right? There can be like switching between, there can be molecules which are switching between these two because of their different temperatures. Because of their different temperatures. Right. Okay. Next point. Write down. If simple n number of, if like this, if simple n number of, if simple n number of water molecules, if simple n number of water molecules if n number of water molecules move to move to move to vapor layer move to vapor layer move to vapor layer same simple n number of same simple n number of same simple n number of vapor molecules simple n number of vapor molecules are moved moved within brackets drops drop moved within brackets drop within brackets drop from vapor layer from vapor layer from vapor layer from vapor layer to to from vapor layer to liquid layer in dynamic equilibrium. From water layer to liquid layer in dynamic equilibrium. In dynamic equilibrium. Right. Next point, use a red pen. For the next point, use a red pen. Next point. Saturated vapor pressure. Saturated vapor pressure. Saturated vapor pressure depends only on. Saturated vapor pressure depends only on. Saturated vapor pressure depends only on temperature. Only on temperature. Second point, keep using red. Second point, keep using red. Saturated vapor mass. Saturated vapor mass depends. Right, check again. Saturated vapor pressure, first point, first point, check the first point. Saturated vapor pressure only depends on temperature. And second point, saturated vapor mass depends on both temperature and volume of container. Second one, saturated vapor mass depends on both temperature and volume of container. Fine. Now, to identify saturated values, we usually put a note like this: P naught and M naught. P naught refers to saturated vapor pressure, right? P naught and M naught. Pressure depends only on temperature, right? So this is only on temperature. Let me do this way. This depends only on temperature, but M naught depends on both temperature and volume of container. Write this down and highlight. Take it down and highlight. This one. Okay, next one. Keep using a red pen again. Right. Then next as the next heading, write down unsaturated vapor. Next heading, second one, unsaturated vapor. Unsaturated vapor. Right. So it is very simple. Compare with this. Now here, maximum number of molecules were already in the air medium, no? Right. Maximum possible number of molecules were already in the vapor medium, right? Then that's why it was saturated. Any additional molecules can be acquired, can be obtained to this layer, right? But when it comes to unsaturated means, as the word says, that is not at the maximum. Which means more number of water molecules can still go to the vapor layer, right? So it was a sudden power cut. I think still the screen is visible and we can manage, right? I guess it is not informed, so it should come back. Should come back in a short while, right? Let's see. Let's see. Now, until then, it's manageable because of this focus light here, right? Write down unsaturated vapor, and write down a vapor. Write down below a vapor able to acquire a vapor able to acquire all right, it came back. Right? A vapor able to acquire more liquid molecules. A vapor able to acquire more liquid molecules. A vapor able to acquire more liquid molecules. More liquid molecules. More liquid molecules. More liquid molecules. Two vapor layer. Two vapor layer. Two vapor layer. Within brackets, not at the maximum. Within brackets, not at the maximum. Within brackets, not at the maximum. Is called unsaturated vapor. Is called unsaturated vapor. Is called unsaturated vapor. Right. Right. Now, as I told you before, all our gas laws like Boyle's law, Charles law, pressure law, combined gas equation, F equals nRT, ideal gas equation, all the gas laws are valid only for unsaturated gases. So unsaturated vapor, right? That is only for unsaturated vapor, not for the saturated ones. Got it? Write down below with a red pen. Write down below with a red pen. All gas laws, all gas laws, all gas laws all gas laws are valid only for all gas laws are valid only for all gas laws are valid only for unsaturated vapor. Valid only for unsaturated vapor. Valid only for unsaturated vapor. Right. Listen. Now, listen. If we really need to apply a gas law, to a system where a saturated vapor layer is already there, right? What we can do is, right, the impact of that is to the pressure, because there is an additional pressure created by the saturated layer, saturated water vapor actually. There is an additional pressure created by them. Now, if I need to apply a gas law to the gas medium, then from total pressure, if saturated vapor pressure is subtracted, if saturated vapor pressure is deducted, then only the unsaturated part remains. Then we can apply gas laws, such like that. Okay, as the next point, write down using red. Next point, keep using red. Saturated vapor pressure should be deducted. Saturated vapor pressure should be deducted. Saturated vapor pressure should be deducted. Saturated vapor pressure should be deducted from total pressure. From total pressure should be deducted from total pressure. Should be deducted from total pressure. If a gas law is applied, if a gas law is applied, if a gas law is applied to a saturated gas, if a gas law is applied to a saturated gas, if a gas law is applied to a saturated gas, okay, take this down as an example. Take this down as an example. Total pressure of a gas is, write down, total pressure of a gas is, total pressure of a gas is P1, P1, P1 at 27 degrees Celsius. P1 at 27 degrees Celsius. In a volume V1, in a volume V1, in a volume V1, in a volume V1. Total pressure, right? Total pressure of the same gas, total pressure of the same gas, total pressure of the same gas is P2, is P2, is P2, P2 at 37 degrees Celsius, at 37 degrees Celsius in a volume of V2, in a volume of V2, in a volume of V2. If saturated vapor pressures, if saturated vapor pressures, if saturated vapor pressures, if saturated vapor pressures at 27 degrees Celsius and 37 degrees Celsius, at 27 degrees Celsius and 37 degrees Celsius are like this: P27 and P37, P27 like this and P37 respectively, P27 and P37 respectively, right? Now in such a scenario, if we are applying a gas law, right, as I told you, saturated pressure part should be subtracted, right, because saturated vapor pressure is not following gas laws, that is not following gas laws, and for the rest you can apply, right? So show how to apply this here, this equation to this given condition by using this data for the combined gas equation. P1 V1 over T1 equals P2 V2 over T2. Try to apply this quickly. Try to apply it. Okay, see, now this is how we should do. Listen, this is how we should do. Now, if I sketch this to get an idea. Now, from this initial stage, right? Initial state temperature is T1. Sorry, temperature is 27. Temperature is 27, right? And pressure is P1. And this volume is V1. Volume is V1, right? And from this at 27 no, at 27 we have a saturated vapor pressure of P27, right? Now saturated part here inside this, the saturated vapor pressure is P27, something like this. And this is our second scenario. In the second scenario, volume is increased to V2, right? This is 37 and total pressure is P2. Saturated vapor pressure at 37 is, right, P37. Right now, when we apply the equation, you have to address that saturated vapor pressure part, because only for the saturated part, gas laws are not applicable, right? Then, if you are applying this as P1 V1 over T1 equals P2 V2 over T2, right? For P1, right, we have to substitute as P1 minus P27. Now it's fine. V1 over T1, 27 means 300, right? And for P2 also, P2 minus P37, V2 over T2 is 310. Got it? Got the idea? So likewise, since our gas laws are valid only for unsaturated gases, if you really need to apply a gas equation, a gas law to a saturated gas, this saturated part should be deducted from total pressure, right? Take it down. Take down the diagram and take it down. Okay. Right. Sorry, I got an urgent call. Right. Let's move on. As an next heading, write down humidity. Humidity. Next heading, humidity. 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 Right. Now, I need your thoughts. What does that mean by humidity? What comes to your mind when we say humidity? I think in my previous explanations also, if you are vigilant enough, right, I explained about what humidity is. What is humidity? What's the meaning? What is humidity? Any thoughts? Any thoughts? Quickly. Any thoughts? What does that mean by humidity? Or what is coming to your mind when we say humidity? Anything? I'm not asking any definitions. What's the idea you have? Humidity. Water vapor. Yes. What else? Water vapor is correct. What else? Right? Water vapor or moisture. Water vapor, moisture. Basically, that's the idea. Humidity means water vapor or moisture. Right? So under humidity, what we are doing is this. Listen. So under humidity, what we are doing is this. This is humidity is the measurement of amount of water vapor available in the atmosphere or in an environment at a given pressure and a temperature. At a given pressure and a temperature. Because if temperature or pressure changes, humidity changes. Got it? Right down below. Humidity is the humidity is the humidity is the measurement on 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 amount of water vapor availability. Measurement on amount of water vapor availability. Amount of water vapor availability in atmosphere. Amount of water vapor availability in atmosphere at a given pressure and temperature. 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 Right. Next point. There are two main types of humidities. Next point. Write down. There are two main types. There are two main types of. There are two main types of humidities. Right. First one is called absolute humidity. Write down. Number one, absolute humidity. Right. This is denoted by XO rho. This is denoted by XO rho. Write down. Absolute humidity denoted by XO rho. Right. Its equation is like this. Right. We can say either rho OX, right, equals MOV. This is the equation of absolute humidity. See, this is the equation of absolute humidity. This is the equation of absolute humidity. Listen first. Absolute humidity is defined as MOV. Right. Now, when we are defining this, we know if dimensions of numerator and denominator are different, we are defining this as considering denominator terms as unit terms. No? right? Same idea, same idea. But here M is not just a mere mass. This is the mass of actual amount of water vapor available in the environment. Mass of actual amount of water vapor available, right? Actual mass, so actual amount of water vapor available. Mass of actual amount of water vapor available is here as M, right? And V is the volume of room or atmosphere, right? Now, if I define these two, don't write, look at here, M. M is mass of or actual mass of water vapor available, right? And V is volume of water vapor, which means behaving volume of water vapor, right? Now, if there is inside a room, volume of the room. If there is in a container, volume of the container, right? So likewise, it changes, not the volume of water vapor. That's the behaving volume of water vapor as a gas. Water vapor is a gas, no? That's why. That's a gas. Water vapor is a gas, right? Then similarities as gases are there. Similarities are there as gases. Okay. Now, take down the equation and highlight to star and introduce these two. Introduce these two. You can ask if any questions, right? So even if you are on the YT Live, YouTube Live, right? Put your questions to the live chat. I can see it. Right? I can see it. Okay, finish. Now we are going to define this. Write down the definition in red. We are going to define this. Write down the definition in red. Right? So basic idea is this is a mass per unit volume, but this mass is the actual mass of water vapor available, and volume is behaving volume of water vapor. Right? Okay, write down the definition in red. Use a red pen. Use a red pen. Write down the definition in red. Actual mass of actual mass of actual mass of actual mass of water vapor available. Actual mass of water vapor available. Actual mass of water vapor available per unit volume. Actual mass of water vapor available per unit volume. Per unit volume. Per unit volume is defined as is defined as is defined as absolute humidity. 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 Right. A small task. A small task. Find units and dimensions of absolute humidity. Find units and dimensions of absolute humidity. Quickly. Find units and dimensions of absolute humidity. Find units and dimensions of absolute humidity. Okay, send your answers quickly. That is easy. Send your answers. Quickly. This is an easy one. Tell me. And by the way, listen. By the way, uh, I was suffering with a heavy headache when I'm starting the class today, right? Now it's okay, right? But I think I explained everything well. If any questions or if there's anything that you didn't get or was not clear in the first part that I explained, right? Please ask, right? I'm not sure whether you notice it or not, but I was suffering with a heavy headache. Not sure what the reason is, but now it's okay. I had some Panadol and now it's fine. Uh, if there's any questions or any doubts, or if there was, if there were anything that is not clear to you in my initial explanations, right? Feel free to ask. That's why I went out and came back. I had some Panadol and came back. Right now it's fine. And me this too. Now 28 batches also started and they are also doing this now. Right? Now you are the uh, senior batch. Right? You are the senior batch among all 26, 27, and 28. Right? You are the senior batch. Right? And just 22 weeks ahead of the exam. Right? 22 weeks ahead of the exam. right? Today is Thursday now, so you got, right, exactly, you got 22 weeks and 3 days, right? Now Thursday is also gone. 22 weeks and 3 days. Most of the standard unit of mass, right, is kilograms. And units of mass over units of volume, standard unit of mass is kilograms, right? And volume is cubic meters. So that is kg m minus 3, right? Same mass and density. This is also density, right? Then dimensions of m over dimensions of v, right? Dimensions of m over dimensions of v. Dimensions of mass is capital M. Dimensions of volume is L cube. Then ml minus 3. Write down below again with a red pen. Write down below again with a red pen. Absolute humidity is 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 the actual density of water vapor. 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 Right. And number 2, like this, I told you there are two types of humidities, no? Right. First one was absolute humidity. Second one is relative humidity. Second one, relative humidity. Second one, relative humidity. Number 2, relative humidity. Right. Symbol used here is Y. Y. Okay. Listen. Relative humidity is defined as this. Relative humidity is defined as Y equals M over M naught into 100%. M over M naught into 100%. Right? M over M naught into 100%. So this is actually a percentage. Right? Relative humidity is a percentage. Right? And there is a percentage of all the values, all the labels we write with the note here in this lesson are the saturated values, right? They are saturated values. And the other values are the actual values. Now, here also the same thing. M means actual mass of water vapor available, actual mass. See, M is actual mass of water vapor available, right? And M naught is always, it refers to the saturated value, right? And this is the required mass to saturate, right? Required mass to saturate the environment. Required mass to saturate the environment. Required mass to saturate the environment. Right? Now basically relative humidity means something like this. Right? This is the ratio between actual mass of water vapor available and saturated mass or required mass to saturate the environment. And there is a percentage value. Now, as an example, let's say in this room, listen, something like this, just to give an idea. Listen, in this room, let's say in this room, actual availability of water vapor now is, right, let's say actual availability of water vapor now is 20. Actual availability is 20. But to saturate this environment, right, to saturate this environment, say the requirement is 50. Requirement is 50, right? Then if I need to do the relative humidity here, that is 20 over 50 into 100%, something like this, 40%, which means this room is 40% saturated. 40% saturated. Right? That's the meaning of this measurement, relative humidity. Something like this. Right? So don't write this part. Take down the heading, equation, and introduce terms. Take down the heading, equation, and introduce terms. Okay, finish. Write down below with a red pen. This is the definition. This is the definition. Write down below with a red pen. Write down the ratio between the ratio between the ratio between the ratio between actual mass of the ratio between actual mass of the ratio between actual mass of water vapor available, the ratio between actual mass of water vapor available and 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 the required mass of water vapor 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 required mass of water vapor for saturation required mass of water vapor for saturation at a given temperature at a at a at a given temperature at a given temperature at a given temperature is defined as relative humidity is defined as relative humidity is defined as relative humidity is defined as relative humidity. Okay, listen. What can you say about units and dimensions of y? What about units and dimensions of y? Huh? That's a mass over a mass, both unitless and dimensionless. Right? Relative humidity is a percentage. That's a percentage. So like this. Just like this, there is a percentage. So it is both unitless and dimensionless. Write down below with a red pen. Write down below with a red pen. Write down below with a red pen. Relative humidity is relative humidity is relative humidity is relative humidity is both unitless and dimensionless. Relative humidity is both unitless and dimensionless. Relative humidity is both unitless and dimensionless. Unitless and dimensionless. Okay, as the next heading, write down equations for relative humidity. Next heading, equations for relative humidity. Equations for relative humidity. Equations for relative humidity. Right. Look at the board. Look at the board. First equation is this, and that is a general equation. Y equals m over m naught into 100%. Right. And same thing can be written using P as P over P naught into 100%. Right. And the same thing can be written using density. Right. Rho over rho naught times 100%. Right. This rho is x. Then x means x over x naught. Right. Both are fine. I told you. Absolute humidity. Right. Then last one. Saturated vapor pressure. Saturated vapor pressure at dew point. Don't worry about what dew point is now because that part is coming now. Saturated vapor pressure at dew point over saturated vapor pressure at room temperature times 100%. Right? These are the, listen, these are the all four equations we have. Right? There are only four. All four equations we have for relative humidity. And when we are solving sums, we are picking the equations from them, from this list, with the availability of data given. With the availability of data given. Right? Write all equations, take down all equations, and highlight all equations. We will be introducing all the terms at once here. That's why I gave you all the equations here. Then you can check all the equations of relative humidity on this single page. On the single page, take it down. Right. Check the equations and the terms again. Right, and take it down. Okay, right? Okay. Now let's introduce these terms one by one. Listen. Listen. We are going to introduce these terms one by one. Listen. Starting from here, I will mention everything here again, even though I have introduced them already, right? I'll be introducing all from here because you can refer this page for all the equations of relative humidity, right? First one, M, actual mass of water vapor available. M, actual mass of water vapor available. M, actual mass of water vapor available. Actual mass of water vapor available. M naught, M naught, M naught, M naught, required mass, required mass, required mass for saturation, required mass for saturation, required mass for saturation, required mass for saturation, slash saturated mass, slash saturated mass of water vapor, slash saturated mass of water vapor, slash saturated mass of water vapor. Right, next one, P, actual pressure of water vapor. P, actual pressure of water vapor. P, actual pressure of water vapor. P, actual pressure. P, actual pressure of water vapor. Right? Actual pressure of water vapor. Slash partial pressure of water vapor. Slash partial pressure of water vapor. Partial pressure of water vapor. Right? P naught, saturated vapor pressure. P naught, saturated vapor pressure. Saturated vapor pressure. Rho, actual density of water vapor. Actual density of water vapor. Rho, actual density of water vapor. Rho naught, saturated density. Rho naught, saturated density. Rho naught, saturated density of water vapor. Rho naught, saturated density of water vapor. Saturated density of water vapor. Saturated density of water vapor. Right. Right. No introduction for these two, that is self-explanatory, right? And about this one, listen, about this one, this row here can always be written as X, right? Write down below with a red pen, put an asterisk mark and write down, row in, row in, row in, y equals rho over rho naught into 100% equation, y equals rho over rho naught times 100% equation. Is absolute humidity. 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 Right. Right. Now, one more important thing. Listen, look at the board. This is the only equation. This one, na? This one is the only equation which links relative humidity and absolute humidity. This is the only equation which links relative humidity and absolute humidity. Right? Keep that also in mind. Right. Okay. So before moving on to the next, raise your hand if everything is clear up to this point. Raise your hand if everything is clear up to this point. And please ask if any questions. It's clear for all of you. Which means I can teach under any given condition. Right? Because I was suffering from that heavy headache when I was running the class. Right? And for like 45 minutes to 1 hour of time, it was there. Right? And now only I feel okay. Right? Now if no questions, which means I can teach under any condition. Okay. Next heading, write down behaviors of relative humidity, within brackets y, behaviors of relative humidity within brackets y, and absolute humidity within brackets x. In a closed environment, in a closed environment. Okay. Listen. This is the core area, right? This is the core area of the lesson hygrometry that we are going to do now. That's the core area. If you understood this part, this whole lesson is nothing. If you understood this part, this whole lesson is nothing, right? To be honest, right? This is the part which is like acting like the heart of hygrometry, right? Now stop all your work and look at the board. Right? If you got this at once, then hygrometry is done. Right? Doing sums, doing questions, applications will be nothing if you clearly understood this part. Right? Listen. Now, as the example room, I will be assuming this room. Right? So let's assume this is a closed room. Right? This is a closed room. I'm going to assume this room. I'm going to assume that room. Right? Now, let's say temperature, current temperature of the room. Let's assume I'm just using some arbitrary numbers to explain this. Let's assume 25 kilo. Temperature of the room is 25 degrees Celsius now. Look at the board. Let's assume temperature of the room now as 25 degrees Celsius. Present temperature 25. Right? Now, from daytime to night time, listen, from daytime to night time, when it goes, temperature decreases, no? That you know. Right? From daytime to night time, temperature decreases. Right? Now, let's say this temperature decreases as 25, 24, 23, 22, 21, 20, 19, 18, 17, something like this. Temperature decreases like this, right? And let's assume the actual amount of water vapor available in this room now as actual mass of water vapor available in this room now as, right? To make it easier, let's assume that as 25 grams at this temperature. Actual availability, say 25 grams. Actual availability is 25 grams. Actual availability is 25 grams. Right. Listen. We know saturated water vapor mass depends only on temperature, no? Right? I discussed that under saturated gases, under saturated vapor, right? We know this. We knew this. M naught depends only on temperature, right? Now, using this equation, I'm going to feed this. M naught depends only on temperature, no? M naught depends only on temperature. M naught depends only on temperature, which means now for the saturation of the room, of this room now, for the saturation, there's a certain amount of water vapor required, right? There's a certain amount of water vapor required for saturation, right? Now, yet, I mean, at the current situation, only 25 grams are available. Only 25 grams are available, right? Let's assume required amount to saturate this environment as 30 grams, right? Now, what I have mentioned here is, this is our temperature, this is M, and here I'm going to mention M naught, right? Since you don't see that part, let me adjust it first. One second. Give me 1 second. Okay, now it's visible. See, listen. Now, this is the temperature of this particular day, and this is M, actual amount of water vapor available, and M naught is the amount of water vapor need for the saturation, right? Now, let's say there is 30 grams now at 25 degrees Celsius. Let's say there is 30 grams, right? Now, if I find the value of Y here at this temperature, see what happens. If I find the value of Y here at this temperature, we know Y equals M over M naught into 100%, right? Find this value. Now it should be M is 25 now. M naught is 30 into 100%. Then these two cancels. 250 over 3. 250 over 3 means 80, 83. Something like 83, no? 83.3. Fine, which means relative humidity of this room now is 83.3%. RH, relative humidity is 83.3. Right, now when temperature decreases, listen, when temperature decreases, according to this equation, when temperature decreases, M naught decreases, no? Amount required for saturation decreases, right? Mass required for saturation decreases. Mass required for saturation decreases. Is it clear? Mass required for saturation decreases. Then let's assume as this decreases as 29 grams, like 28 grams, 27 grams, 26 grams, 25 grams, 24 grams, 23 grams, 22 grams, and 21 grams, something like this, because when temperature decreases, M naught decreases. I assume some values, arbitrary values for the explanation. When M naught T temperature decreases, M naught decreases. Right, now listen about, think about this room. Right, think about this room. If temperature decreases from 25 to 24, right? If temperature decreases from 25 to 24, right? What can we say about actual amount of water vapor available? Water vapor availability is in the room, in the vapor layer somewhere here, in the vapor layer somewhere, in the sense it is vapor layer is above, right? That is above, that is in the vapor layer. Now, right now, even though temperature decreases, this 25 grams which was there in the vapor layer remains safe. 25 grams which was there at the vapor layer remains safe, right? Which means at 24 also my availability is 25 grams. At 23 also availability is 25. 22 also availability is 25. And 21 also availability is 25. Right? Right? Now, can you see how this trend goes? Can you see how this trend goes according to this equation? Right? Now, if you check this, Y equals M over M naught into 100%, no? Now, what is happening is M remains constant. M remains constant. But M naught decreases. M naught decreases. Then as a result, Y increases, no? Y increases, which means Y is in an increasing trend. Right? Which means Y is in an increasing trend. Y is in an increasing trend. Is that clear enough? Raise your hand if it is clear enough up to this point. I just started the explanation. And these numbers are arbitrary numbers. Numbers are arbitrary numbers for the ease of explanation. Right, clear. Right. Now, at 20, see, this is kind of a special. At 20, my availability is 25 grams. Let me write this in the same line properly. This was 26. This was 25. And for this line, 24. For this line, 23. And for this one, 22. Okay. Right. Here, see, now at 20 degrees Celsius, actual availability was 25 grams. And requirement for saturation is also 25 grams. Correct. Requirement for saturation is also 25 grams. Now, in that case, if I check Y, what has happened to Y? Y is M over M naught into 100%. Right? Now, M is also 25, M naught is also 25 into 100%. Right? Which means Y equals 100% no? At 25. Y equals 100%. 100% means that is called a saturation. That is called a saturation. Now, these ones are 83 means that is partially saturated. For 80% or for 83% that is saturated. But still there is more room, more space to acquire more water vapor, right? 100% means now it is saturated. Now it is saturated, right? And at this temperature, listen carefully, at this temperature, this actual amount of water vapor available was just enough to saturate the environment. No? Got it? Actual amount of water vapor available was just enough to saturate the environment, right? That particular temperature is called, that particular temperature where actual amount of water vapor is enough to saturate the environment is called the dew point, right? So dew point today is, in my example is 20. Dew point today in my example is 20, right? Repeating again, the temperature at which actual amount of actual mass of water vapor available is just enough to saturate the environment is called dew point, right? Now actual availability was 25 grams. No, the temperature at which 25 grams is enough to saturate this environment is called dew point. Got the idea? Raise your hand if you understood that. What dew point is? Feel free to ask questions if any. Okay, right. Super. Now this is called the dew point. And at dew point, something important, listen, something important. Y is 100% now. Y is 100%. We started from here, and from here to here, we knew that Y increases. From here to here, we knew that Y increases. And now at 25, at 20 degrees Celsius, not 25, at 20 degrees Celsius, Y has reached 100%. That is called a saturation. That is called a saturation, right? Now, even if the room reaches the dew point, cooling won't stop, right? Always the environment or the room, right, atmosphere is cooled beyond the dew point, right? Beyond the dew point. Now, see what is happening. Very important. Look at the board. Look at the board. Now, actual availability we have is 25 grams, but the requirement is only 24 grams. Listen again. Actual availability we have in the room now is 25 grams, but actual requirement to saturate this is 24 grams. Requirement to saturate this is 24, just 24 grams, right? Now, if you try to apply that in the equation, you are going to get something greater than 100, right? You are going to get something greater than 100, right? That is wrong. So actually what happens is this. Now a redundant amount or extra mass, right? Extra mass is available beyond saturation, no? Because for saturation only 24 grams are needed. But in this room I have 25 grams available. Then what it does is this. Listen carefully. What it does is this. Only 24 grams will be kept at vapor layer, right? Only 24 grams will be kept at vapor layer to saturate the environment. And this additional 1 gram is condensed into water. Condensing means water vapor is a gas, no? Water vapor is condensed to water. And once it is condensed to water, it falls down from that vapor layer. It falls down from the vapor layer, right? Water vapor is somewhere here, somewhere above. Water vapor, that's a gas, no? Water vapor is a gas. But condensed water means there is water droplets. Condensed water means water droplets. Then they won't stay as a gas, they falls down. They falls down to the floor. They falls down to the ground, right? And that condensing of water vapor into water is called dew, forming dew, right? That is called dew. DEW, dew. That is called dew. Then from this 1 gram, it is converted to dew. It is converted to dew, right? That is why this point is called dew point, because that's the point where forming dew is starting. That's the point where forming div is starting. Right? After that point, the mass which is required for saturation will only be kept in the air medium, right? In the vapor medium, and the additional part, right? The additional part, redundant part, is condensed into div and put it down from the vapor layer, right? Put it down from the vapor layer, right? That is div. That is how div forms. That is how div forms. And we can see div on each and every morning, right? If you are walking in mornings before like 8:30, around before 8, right? If you walk in the morning, if you take a walk in the morning, right? Maybe you are going to the school. When you are going to the school, if you notice, dew can be seen on leaves, right? On leaves and all that. That is because the last day night dew point has been passed and dew has formed, right? And dew has fallen to the ground. Because now this same thing that I explained using this room is valid for entire universe, entire Earth, entire universe. Got it? Same thing that I explained using this isolated room is valid for our own Earth, right? Earth එක වෙන්න තෝකමයි. That's the same thing, same process as a big picture. Same thing happens. That's how we see div in the mornings, right? Okay, I'll explain about that further in the coming parts. Right, let's move on. Now, when it is come to 18 degrees Celsius, 18 degrees Celsius, now what's the availability? What is the availability of the environment now? Availability of the environment now is 24 grams, only 24. But requirement is 23. Then what this does is 23 grams is kept to saturate this, and this additional 1 gram is put down again. The additional 1 gram is put down again as dew. And at 17, requirement is 22. We have 23 grams. Then only 22 grams will be kept at the air medium. And this additional 1 gram is again put down as dew. Then at the end of the process, right? At the end of the process, right? 3 grams of dew is formed. At the end of the process, 3 grams of dew is being formed. 3 grams of dew has been formed. Now, if I check y beyond this point, can you see? Always 24 to 24, 23 to 24, that is balanced, which means y remains same at 100. Y remains same at 100. Right? Y remains same at 100. So before going on to the absolute humidity, behavior of absolute humidity, raise your hand again if you are clear about what I explained up to this point. If any questions, ask anything. Ask anything if any questions. No questions? Won't the temperature decrease further below 17? No, I considered that as 17. Now, in a particular day, there's a lowest temperature it reaches, right? There's a lowest value for temperature it reaches in a particular day. Now, today I considered that as 17, right? And it changes day by day. Now, for this particular example, I considered that as 17, right? There's a minimum temperature, a lowest temperature reached at the end of the day, right? There's a minimum and a maximum temperature, right? I considered for today, for this example, actually, it has 17. That's why. What else? Any other questions? Ones on YouTube? Any questions? Ones on YouTube? Any questions? If anything, feel free to ask. Okay, if no questions, we can move on. See, now the next thing is about absolute humidity. Listen, we know equation of absolute humidity is, look at the board. Equation of absolute humidity, that is X or O. X is MOV, no? X is MOV. Absolute humidity is MOV, right? M, actual mass of water vapor available, right? Now from here to dew point, see, look at here. See what happens from here to dew point. Actual mass of water vapor available remains same. 25 grams, 25 grams, 25, 25, 25, 25. Actual mass of water vapor available is same. If actual mass is same, M is constant. And I consider this room. Volume of the room remains unchanged, which means X remains unchanged. No? Is that clear? Which means X remains unchanged. So up to dew point, absolute humidity is constant. Up to dew point, absolute humidity is constant. After dew point, see what happens. After dew point, X equals M over V. After dew point, actual mass of water vapor available in the atmosphere decreases. Actual mass of water vapor available in the atmosphere decreases, which means M decreases. But that's the same volume, same room, same volume, which means X decreases. No? So therefore, X decreases. Right? X decreases. Again, if we start from here, from the current temperature, right, up to dew point. Now this was our dew point. This was our dew point. This was our dew point for today. This changes day by day. This was our dew point for today. This was our dew point for today. Right? Up to dew point, Y increases. See the difference? Y increases while X remains constant. At dew point, Y is 100%. At dew point, Y is 100%. Beyond dew point, Y is constant. Y remains constant at 100%. Y remains constant at 100%. And X decreases. Got it? That is what is happening. Right? Now, this same thing I explained using this room. Right? We can take it to the big picture of the earth. Right? So day to day, when sun rises and sun sets, what happens is this. Right? Day to day, in daily basis, what happens is this. Right? Now temperature decreases. When temperature decreases, at a certain temperature, the atmosphere reaches the dew point. After the dew point, dew forms. Right? Dew forms, and we can see dew during the night times. Right? And beyond the dew point also temperature decreases and it reaches a minimum value. Right? Minimum value. And when sun rises again, the exact opposite cycle goes. When sun rises again, exact opposite cycle goes. Then what happens is something like this. Now, when sun rises, when temperature increases from 17 to 18, look at here. When temperature increases again from 17 to 18, requirement is 23 grams. But in the atmosphere, it had only 22. But there was 3 grams of dew, no? There was 3 grams of dew. Then again what happens is 1 gram from this dew is also water, no? 1 gram from this dew is again converted to vapor and coming to the vapor layer. And it satisfies 23 to 23, 100%. And again when it goes from 23 to 24, again 1 gram from dew is taken here and satisfied. And for 25 also, another gram is taken from here and satisfied. But again, after this point, it is helpless. Even though the requirement is 26 grams, actual availability of all water in the atmosphere is only 25 grams. Then no dew is there anymore. Then again, this cycle goes up, increasing temperature. And it reaches the maximum possible temperature for that particular day. And again at the night time, during the night time, again the opposite process happens. Again in the daytime, the opposite happens. So likewise, this is an unending cycle, never ending cycle. that we have, right? In daily basis, this changes, right? And in all days, dew point is reached. Dew point is reached. Always dew point is reached during the night time, and usually the temperature falls beyond dew point as well, right? That is what happens. And if I explain a little bit about the practicability of this, right? If I explain a little bit about the practicability of this, if you are using any weather apps, right? You can see these things in weather apps. Now, since you know the lesson hygrometry, now you can see what is given here. Let me show you from mine, right? Then you also can check with your device, right? What about the temperatures today? Temperature. Mm, 1 second. Okay, see, it's visible, right? Visible now. Now this says highest temperature of today is 32, right? For this location, now for this location, and lowest temperature today is 24, right? Lowest temperature today is 24, and if I need to check the dew points and other data, check the dew points and other data. See, now dew point is given. Before that, humidity is given. See, humidity for today is 72%. Now, humidity in this area now is 72, which means requirement for saturation is greater than the actual availability. That is how it happens. Now it is only 72%, right? So as humidity, what is given in these apps is apps are RH, relative humidity, right? Not the absolute value. Relative humidity 72%, right? And it says dew point today is 24. See, dew point today is 24, right? Dew point today is 24, which means at 24. Now what's the current temperature? Current temperature is 29. Current temperature is 29. Now when we are moving towards the night side, right? What happens is temperature drops and it reaches 24 at some point. No, listen, temperature drops and it reaches 24 at some point. When it reaches 24, it starts forming dew. Today, right? And when temperature falls beyond 24, right? When temperature falls beyond 24, right? Now in this particular app, it showed as 24. That is because the decimals are not given, right? For sure, it is decreasing beyond 24. 24 means beyond dew point, right? Now, as an example, if dew point is 24 point, say 8 today, and lowest temperature reached by the day is 24.2 or something like that, right? I couldn't find how to turn on the decimals. Otherwise, we can see these values, see those values, right? And let me check for some other areas as well, because now for today in this area, this is more like rainy, right? It's better if I can check a kind of a sunny area. What are sunny areas these days? What about Kandy, Gogantalawa? Who else? Varakapola. What about those areas? Gampola. Tell me any sunny area to check this out. What about Kandy? You also can check from your weather app if you are using a weather app. What are the sunny areas? Hmm. 1 second. Let's check candy. All right. See, very. Now this is about candy, right? Candy. Current temperature is 28. Current temperature is 28, right? And humidity now is 62. Humidity now is 62%. And dew point today is 20 degrees Celsius, 20. And lowest temperature reached by the day is 19. That is 19. Can you see? Right? That is what usually happens. That is what usually happens. Always, the minimum temperature reached by the day is less than dew point. Now, regarding the scenario of candy, right? Now, for candy today, right? Today after 20 degrees Celsius, forming dew starts, right? Forming dew starts, right? If needed, we can check the times as well, right? Make it, you can check the timeline of temperature. Then from that, you can check at which time this is going to reach that temperature. Listen. Then let's assume that as 2 a.m. at 1 a.m. Candy is reaching 20 degrees Celsius. Then after 1 a.m. forming dew starts. After 1 a.m. forming dew starts. And when temperature decreases further up to 19 degrees Celsius, dew forms. And when the system comes to the opposite direction, again the opposite takes place. And this happens at daily basis. Right? That is how you see dew in the mornings. Right? And that is how dew is disappeared once sunlight falls. Once sunlight falls, dew disappeared because of this. Because when temperature increases, requirement increases, then all the dew is vaporized to vapor layer to maximize this value, and then temperature increases once all dew are come into the water layer. Sorry, vapor layer. Something like that. This is the process which takes place in each daily basis in this environment, right? And dew points, maximum temperatures, minimum temperatures, those things are getting varied day by day due to various reasons, like wind speed, right? Amount of sunlight falls, right? So likewise, because of various reasons, it can be different. The actual amount of water vapor available now for today, say actual amount of water vapor available is 25 grams, and say for tomorrow, actual amount of water vapor available is 26 grams. Then if there is 26 grams, dew point of tomorrow is 21. Got my point? Right? Say day after tomorrow, actual availability of water vapor in the atmosphere is, say it is only 22 grams. Then in that particular day, dew point is 17 degrees Celsius. Right? So likewise, dew point also changes day by day. Right? Now since you know the subject, now if you are using any devices, any weather apps, right? Just go into the weather app, right? Dig deep, right? And check where the dew point, humidity, and those things are mentioned, and get some idea about what's happening around. That's the practicability of this. Right? Okay. Raise your hand if it is clear about all these things I explained here. This is the core of this lesson. This is the core. This is like the heart of the lesson. If you understood this properly, doing sums is very much easy. It's nothing. How many of you? Is that all? Who else? Oh, okay. Right. Now take this down. You better use a single page and take this down. I will give you the explanation of this after this. Fine. Take this down. I checked, sir, in our area, humidity is 74%. Yeah, good. 74% now. Now the time is like 6:09. 74%. Then when you are going towards the night time, right, temperature decreases and humidity increases. Now, if possible, you can keep on checking the humidity by hour, right? hour on hour you can check and get an idea how it increases. It increases when you go towards the night side, like this. Now at present, now if you say 74, right? If you check this after the class, right, it probably should be greater than 74. And if you check it at 12 a.m., should be greater than that value. And at 1 a.m., 2 a.m. should be greater. So likewise, you can check it out if needed. Good. Take it down. Use different colors if possible, because this should be 100% clear to you. This should be 100% clear to you, right? You are the one is going to refer this again, so make it clear to you. Sorry. Okay, finished? Finished? Have you finished taking down? Have you finished taking down? Raise your hand if you finished. I'm checking to move on. Okay, finished off? Right. Okay. Before explaining the next part, we'll get the break because our Muslim students needs to break their fast now, no? Right? 6:17. Let's have a break. Keep this in mind when you are coming after the break because I'll be explaining the rest after the break. Explaining means I didn't give you any notes on this yet, right? We'll give this note after the break. Now it's 18 now. We'll get a break of 20 minutes. 20 minutes and come back by 6:38, right? So you can go refresh yourself and come back by 6:38 and keep this in mind, keep this store in mind, and if possible you can check these values now for your area and get some more understanding, right? Okay, let's meet after the break and regroup by 6:38. Okay, sorry. Okay, sorry about it. Sorry about it. Now it's fine now? Okay. Right. See, now what we have discussed up to this point. What we have discussed up to this point is, right, when this goes from day to night time, daytime to night time, temperature decreases, right? When this goes from daytime to night time, temperature decreases, right? So likewise, now I have started at 25 and I assume that lowest temperature it is going to reach in this particular day as 17, right? Now temperature is going to decrease from 25 to 17. Temperature is going to decrease from 25 to 17. And we know M naught required mass for saturation or saturated mass is also a variable of temperature. It's also a variable of temperature. Then the higher the temperature, higher M naught, lower the temperature, lower M naught, because that is directly proportional. Right? Then with this temperature decrease, I assume that M naught decreases as 30, 29, 28, 27, 26, 25, 24, 23, 22, likewise, right, up until 17. And as M, listen, as M, what we have mentioned is, actual availability of water vapor in this environment, actual availability or the actual mass of water vapor. In the environment, right? Actual mass. Now, it was 25 at the beginning. Right? Now, even though temperature decreases, actual availability of the atmosphere remains same. Now, it was 25, remains same even when temperature decreases. And we check this behavior using this equation for y. Y is m over m naught into 100%. M over m naught into 100% times 100%, right? M over m naught times 100%. And if I apply that in the equation, right, initially we got a relative humidity of 83.3, right? And if you apply it for the second case, right, 25 or 29, no, 25 or 29, then it will be a value greater than 83. I didn't check, I checked the behavior here, right? For sure that value is going to be greater than 83 because when m naught decreases, right, according to the equation, y increases. When m naught decreases, y increases. According to the equation, when m naught decreases, y increases, right? Y increases, right? And at one particular point, very special and important, at one particular point, the actual availability and the requirement to be saturated are getting equal, right? At one point, the actual availability of water vapor and the requirement for saturation are getting equal, right? At that point, at that exact point, what happens is this: M and M naught are same, then relative humidity is 100%. Relative humidity becomes 100%. Right? And this particular temperature, 20 degrees Celsius, right? In this example, that is 20 degrees Celsius. That is called the dew point. Of this particular day. Right? We had 25 grams as the actual availability in the atmosphere, and the temperature at which that 25 grams is just enough to saturate the environment is called dew point, right? So if that was enough to saturate the environment at 15 degrees Celsius, we call 15 degrees Celsius as the dew point, right? Now, tomorrow, if the availability of water vapor was say 27 grams, if it was 27 grams, right, then requirement to saturate becomes 27 at 22. Then for tomorrow, dew point becomes 22 degrees Celsius. So likewise, with the actual availability of water vapor in the atmosphere, dew point changes day by day, right? With the actual availability of water vapor in atmosphere, dew point changes day by day. right? If actual availability of water vapor is say 23 grams today, if it was 23 grams, 18 would be 18 will be the dew point. So likewise, dew point changes, right? So repeating again, dew point means that is the temperature at which actual availability of or the actual mass of water vapor available in the atmosphere is enough to saturate the environment at a given temperature at a given pressure. That is called the dew point. Right now, in this particular example, 20 degrees Celsius is the dew point. But this process is not going to stop even though it has reached the dew point. Always the environment is cooled, right? It's get cooled beyond the dew point. It gets cooled beyond the dew point, right? Which means now even though dew point of today is 20 degrees Celsius, right? Temperature of the environment drops further. It drops further, right? Now, after dew point, what is happening is, right, after dew point, now at the dew point, we had 25 grams available in the vapor layer. At dew point, we had 25 grams available in the vapor layer. 25 grams in the vapor layer, right? 25 grams in the vapor layer. But at 19 degrees Celsius, our requirement is only 24 grams. Our requirement is only 24 grams. Requirement is only 24 grams. Then some additional amount, redundant amount, extra amount of mass is available. So what the vapor layer does is, right, from this 25 grams, 24 grams are kept at the vapor layer for the saturation, right? Because if it is available, always the vapor layer is trying to be saturated. Always vapor layer is trying to be saturated if the availability is there, right? Now, when there is 25 grams, for the saturation only 24 grams is required. Then 24 grams is kept at the atmosphere, right, at the vapor layer, and that additional 1 gram is condensed. When water vapor is condensed, it forms water. When water vapor is condensed, it forms water, right? And water means dew. Then after this point, this additional 1 gram is put down from vapor layer as condensed dew, right? This additional 1 gram is put down from vapor layer as condensed dew. And when it is coming to 18 degrees Celsius, requirement is 23 grams and the availability now is 24 grams, right? Another 1 gram is redundant. Then only 23 grams is kept here, and that remaining 1 gram, additional 1 gram, is also condensed and put down from vapor layer as dew. And when reaching 17, requirement is 22 grams, and the availability at 18 is 23 grams, right? Then only 22 grams will be kept here, and that additional 1 gram is condensed into dew and put down from vapor layer. At the end of the process, 3 grams of dew has been formed. Right? At the end of the process, 3 grams of dew has been formed in this particular example. Right? This is what happens when we move from daytime to night time. Right? An exact opposite happens when we move from night time to daytime. Right? So likewise, this cycle continues. Right? This cycle continues in all days, in a daily basis. Right? And because of that reason, dew point, availability of water vapor in atmosphere, and everything changes day by day, right? Everything changes day by day, right? Now, since this is clear, let's take down the note, right? Mention this way. Mention as the first bullet point. When temperature decreases up to dew point, first bullet point, bullet top, you can put an asterisk mark. When temperature decreases up to dew point, the, when temperature decreases up to dew point. Okay. Respond now. When temperature decreases up to dew point, what about y? What's happening with y? Increasing, decreasing, or constant? What about y? When temperature decreases from here to dew point. What about y? Quickly. Respond. Please respond. Oh, I have explained everything already. What about y? Y increases. Y increases. Y increases. Right? When temperature increases from here to dew point, up to dew point, what happens is m naught decreases. When m naught decreases, y increases. Right? Dew point. Put a comma and write down below. Right? Under this bullet, now you have written this in a bullet, no? When temperature decreases up to dew point. Under that, first point, use a red pen. First point here, use a red pen. Write down. Relative humidity increases. Relative humidity, first point here, right? Relative humidity increases. Relative humidity increases since m naught decreases. Relative humidity increases. Relative humidity increases since m naught decreases. Relative humidity increases since m naught decreases. Okay, mention this equation along with that y equals m over m naught into 100%. Right? Now, since m naught decreases with temperature, y increases. Right? And you better mention this as well, m naught proportional to t. Like this. Mention both the equations. Mention both the equations. Right? Second bullet point here. Tell me, what about absolute humidity? What's the behavior of absolute humidity up to dew point? What's the behavior of absolute humidity up to dew point? Respond. Respond. What's the behavior of absolute humidity up to dew point? Increasing, decreasing, or constant? It's constant. Good. It's constant. Right? That we checked here. That is constant because m is constant. Right? Then next bullet point. Use red this one. So under the main bullet point, we are in the sub bullet points. First one is done. The second one write down. Absolute humidity remains constant. Absolute humidity remains constant since simple m remains constant. Since simple m remains constant. Absolute humidity remains constant since simple m remains constant. Right. So we can explain it using this equation. Right. Mention this for the second bullet point. X equals m over v. Right. M over v, and m is constant. when m is constant, x is also constant for a given closed room. For a given closed room, right? Okay. Then second main bullet at dew point. Second main bullet at dew point. Second main bullet at dew point. At dew point. Right. Tell me, what can you say about relative humidity at dew point? Relative humidity at dew point. What about it? 100%. Right? 100%. Relative humidity at dew point is 100%. And about absolute humidity is still remains constant. Absolute humidity is still remains constant. Right? Absolute humidity is still constant. Right? And dew point is 100%. Sorry, relative humidity is 100% at dew point. Right? Then at dew point, sub bullet 1, write down in red, write down in red. Relative humidity equals 100%. 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 Right? Second bullet point. Absolute humidity still remains constant. 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 Okay. Then next main bullet. Write down when temperature decreases beyond dew point. Write down when temperature decreases beyond dew point. When temperature decreases beyond dew point. Right. Beyond dew point. And sub bullets. First tell me what's happening with relative humidity when temperature decreases beyond dew point. What happens with relative humidity? Huh? What happens with relative humidity when temperature decreases beyond dew point? What's happening? Increasing, decreasing, or constant? Relative humidity beyond dew point, that is constant at 100. That is constant at 100. Right? And what about absolute humidity beyond dew point? What about absolute humidity beyond dew point? What about absolute humidity beyond dew point? Huh? Yeah, it is decreasing. Right? Absolute humidity decreasing. Okay. Then first sub bullet here, write down relative humidity remains constant at 100%. Relative humidity remains constant. Relative humidity remains constant at 100%. 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 right? Relative humidity remains constant at 100%. Second bullet, absolute humidity decreases using red. Using red. I wrote all these sub bullet points using red, right? Second one, absolute humidity decreases. Absolute humidity decreases since simple lem 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 decreases. Right. Mention the equation again. X equals M over V. Right. X equals M over V. When M decreases, X decreases. Right. Next point. Next bullet point. Keep using red. Bullet in the sense sub bullet. Right. When beyond dew point below the same bullet. Third sub point. The third sub bullet. Write down. Redundant amount of water vapor. Redundant amount of water vapor. Redundant amount of water vapor. Redundant amount of water vapor is condensed to is condensed to is condensed to is condensed to water is condensed to water as dew is condensed to water as dew is condensed to water as dew and put down and put down and put down and put down from vapor layer and put down from vapor layer and put down from vapor layer put down from vapor layer while keeping while keeping while keeping while keeping the saturation at 100% 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 while keeping the saturation at 100%. Right. Okay. So that's everything we discussed from this part, right? From this part in the sense about these behaviors of X and Y, behaviors of X and Y, right? And now let's define what dew point is. Now we know, right? We didn't write it now. Next heading, dew point. Next heading, dew point. Dew point. Dew point. Okay, write down the definition. Write down the definition of dew point. Write down the temperature at which the temperature at which the temperature at which the temperature at which actual mass of water vapor available at which actual mass of water vapor available actual mass of water vapor available is just enough to is just enough to saturate the environment. Is just enough to saturate the environment. Is just enough to saturate the environment. Is called dew point. Is called dew point. Is called dew point. Is called dew point, right? And as another point, write down below. Write down below as another point. Relative humidity at dew 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 point is 100%. 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 Right. Relative humidity at dew point is 100. Right. Listen. Now, after this part, right, we are going to plot some graphs in hygrometry. Right. So first, I'll be separating this, segregating this into two as saturated gases and for saturated vapor and unsaturated vapor, right? And then we'll be seeing how these graphs are connected from saturation to unsaturation, no unsaturation to saturation, right? As the next heading, write down graphs in hygrometry. Next heading, graphs in hygrometry. Graphs in hygrometry. Under that, as number 1, write down for unsaturated vapor. As number 1, write down for unsaturated vapor. For unsaturated vapor. Number 1. Under that, number 1 for unsaturated vapor. For unsaturated vapor. Right. Now, tell me, when it comes to unsaturated vapor, do they follow gas laws? Yes or no? What about unsaturated vapor? Do they follow gas laws? Unsaturated vapor. Yes. Right? Yes. Yes, they follow gas laws. Unsaturated part follows gas laws. Right? Then almost all of these curves that we are going to see now are already being plotted under gases, right? Under gases. Gases are also unsaturated, no? Right? Now here also you are going to get same curves, right? First I will give you all curves, right? And give you some time to plot all curves, right? Start plotting one by one. For unsaturated ones we have already done. We have already plotted under gases. Then I'm not going to discuss this that in detail because we did this already in gases. First one P with V. Second one P with 1 OV. Right? And next one P with T. Right? P with T. Or make it theta. Theta means degrees Celsius. Then next one V with theta. And next PV with V. And PV with P. Plot these curves. I will give you like 2-3 minutes. But these curves, they are for unsaturated gases. Okay, finished. Finished. Let's see. Okay. Co-unsaturated means when they follow gas laws, right? Then PV. PV means if we are plotting PV, T is a constant. Then this follows Boyle's law. This follows Boyle's law, right? We have discussed how to plot them. It follows Boyle's law. Then for this particular graph, Boyle's law means PV equals K, no? PV equals K. Then P is K 1 over V, right? We are plotting P and V. P is as Y now and V is X. Then this is like Y equals M1 over X, right? It is like Y equals M1 over X, inverse curve. So this is an inverse curve. So likewise, you have to check one by one and plot them, right? Inverse curve. Next, P with 1 over V. Same thing. From Boyle's law, P equals K 1 over V. Now whole thing 1 over V is considered as X. This is M. This is Y. So that is Y equals Mx. That is Y equals Mx. Y equals Mx. Fine. Next one. P with theta. Theta is Celsius temperature. Right. If you are plotting pressure and temperature, which means volume should be constant. No? Volume is constant. Which means this follows pressure law. This follows pressure law. Volumes are constant. Right. What is coming from pressure law? P equals P over T equals K, no? Pressure law. Right? P1 over T1 equals P2 over T2. P over T equals K. Then it says P equals KT. Right? Now to convert this Kelvin temperature to Celsius temperature, we can use Celsius temperature plus 273. Now P equals K theta plus 273 K. Right? Identify variables. This is X and this is gradient plus this whole thing is intercept. This is Y. Y equals mx plus c. Y equals mx plus c. Mx plus c. Right? If you extend this to this side, right? If you extend this to this side, the temperature here is going to be minus 273. Right? If you extend, right? If you need to find this value, make P0. Make P0 and find out theta is minus 273. Then V with theta. V and temperature changes, which means pressure is constant in this graph. Pressure is constant. Right? Then Charles law is valid. Charles law. V over T equals K. Charles law. Then V equals KT. Do the same conversion. Right? Do the same conversion. Then V equals K. T is theta plus 273. No? Right? Identify variables. This is, let me write here, V equals K theta plus 273 K. Theta is X. Theta is our X. This is M. This whole part is C. This is Y. Mx plus C. Mx plus C. 1 second. Right. Mx plus C. Right. And PV with P. PV with V. If you are plotting PV with V, which means temperature is constant. If temperature is constant, Boyle's law is valid. PV equals K. Product PV is a constant. Then if there is a constant, whatever the value of V, PV is a constant. Whatever the value of P, PV is a constant. Product PV is a constant. Right. And next one, PV with P. P with P. Still temperature is constant. Then Boyle's law is valid. PV equals K. PV is a constant. Okay. Make changes if anything. Correct them. Make changes if anything. And when it comes to these unsaturated graphs, right, we plot them today for the second time because I have plotted the same under gases. Okay, right. Right. Keep the next heading written as for saturated vapor. Next heading as number 2. Keep this written number 2 for saturated vapor. For saturated vapor. Number 2 for saturated vapor. Right. Right. Listen. Right. Listen. So we have finished almost all theories except the graphs for saturated vapor, right? That's a small part remaining now, right? And for that part, it will take like 30 more minutes, right? Something like that. And next day, our main plan is we'll be discussing all types of sums, questions from hygrometry. And we are going to finish off hygrometry by next day, right? Next week, we'll be finishing hygrometry. And after hygrometry, I'll be starting thermal conduction or heat conduction. And after heat conduction, thermometry. And we'll be finishing thermal. We'll be finishing thermal physics. And in the reverse class, since first part of radiation is already finished, we are starting black body radiation this Saturday. Black body radiation, right? And after black body radiation, in the reverse class, the other lessons coming up are photoelectric effect, X-ray production, and laser production, right? Those things are coming up, right? And I didn't fix a time for S2 discussion tomorrow because I'm not sure whether I will be available tomorrow at 8, right? Let's see. If I was available, if I'm going to be available tomorrow, I'll be conducting the S2 discussion most probably on viscosity, right? Most probably it will be on viscosity, and you can get all updates through channels, right? I didn't inform yet because I'm not sure whether I'm available. I will be available tomorrow during that time this week, right? Let's see. Yeah, those are the things coming up. And you are 22 weeks and 3 days ahead of the exam now. And soon I think you have your first terms as well, right? Grade 13 term 1 first term is also there, right? So study hard, work hard, and write papers and come to paper discussions, and you can try all the papers that we have already discussed in the paper classes, and go to the exam, right? And go to the exam, sit for the exam, right? Okay then. Any other questions about what we discussed today? Any questions? Any questions about what we discussed today? Is there anything to know or any clarifications needed? Any questions, any doubts? Or is it all clear? Or is it all clear up to this point? We are like 95% of theories in hygrometry is over. 95% is over. 95% is over. We still have, I mean, we have yet to do the graphs. That's only the graphs. 95% is done, all clear. All clear. Right. So if no questions, I will wind up. Right. See you in the next class. Stay safe and work hard these days. Even a single second you waste is going to matter your final result. Right. This is definitely something doable. Definitely something doable. Right. As long as you have that courage and consistency when working. Right. You have to have that courage and the consistency. Right. Consistency is one of the main keys here. If you work like on and off, that is not going to work. You have to be consistent, right? Okay, so study hard, work hard, and see you in the next class. Good night and goodbye.